Well, hopefully that wasn't too hard for you to kind of go through this concept of, you know, particles coming together because of gravity, compressing, burning because of nuclear fusion, and running out of fuel, collapsing, and exploding. That's kind of just how it goes, right? Like, that's the main thing that happens in the universe. We've got nebulae and all these sorts of things we can observe now. But we talked about this starting 13.6 billion years ago, which means it's been going on for a long time. Another thing to consider is the size of that cloud, the initial kind of dust cloud, or you could think about it as, you know, hydrogen, helium atoms. The larger the pool, the faster the star will burn. So some stars will go through kind of birth to death in maybe a couple of 100 million years, whereas some that are smaller may kind of sustain. They won't burn through their fuel or won't burn quite as bright. But anyway, this is a climate change class, and I'm not forgetting that. But I do like to drag you through some of this stuff. So as this is happening in these stars over and over and over, new elements are being born, things are being blasted out into space. The overall composition of the universe begins to slowly change. Which is initially, you know, 97% hydrogen, 3% helium. But over time, that hydrogen begins to get consumed, and some of it's consumed and produces helium. But in the larger stars, they have enough energy to fuse helium, to fuse carbon, to fuse oxygen, to fuse some of these elements that are higher up in the periodic table of elements. And when they do, they make more complicated elements, larger atoms, and those larger atoms get blown out into the atmosphere, or blown out into the universe, and those are incorporated into the next generation of stars in any particular area. So the composition starts to change, and we start to get larger particles. When we get about, not quite 10 billion years down the road, about 9 billion years after the Big Bang, and this process has just been going on and going on and going on, we start to get another process that now we realize is basically trivial. It happens everywhere all the time, but this one matters to us. And so the same cloud, the same process begins to occur. You get enough mass, these particles are kind of compressing, and eventually starts a new star, right, when that fusion reaction happens. But this time, it's ours. And this happens about 4.5 billion years ago. And when that happens with our sun, there's still a bunch of rocky debris and particles and things like that that have formed, and they begin to rotate around the sun. The cloud's rotating the whole time, and it starts to form what we call an accretion disk. And so there's, you know, hundreds and thousands of small rocky bits orbiting around the sun. But remember, universal gravitational constant. So in that disk of rocky bits, there starts to be collisions that start to build larger and larger masses. And as those larger masses are traveling around the sun, they're vacuuming up smaller particles. Now, eventually, those particles get to the size where they start to change fundamentally, internally. Prior to that, we call them planetesimals. But eventually, when these things get to the size where they start to have their own physics and chemistry operating within these piles of rocks, that's when we get to the point that we call true planets. So again, that happened to Earth about 4.56 billion years ago with the B. It's a long time ago. And in that debris, right, in that kind of accumulating mass, there's basically everything, right? There's hydrogen in there, there's helium in there, there's heavier minerals, there's silicates, there's all kinds of stuff in this mass. And the cool thing is this project, and the cool thing is this process is still going on. Although, now that our solar system is fairly old, as our planet is moving around in our solar system, it's still drawing in this kind of primordial kind of original material that was part of our solar system that never got picked up. Those are shooting stars, right? Meteorites. Those things happen, right? They hit Earth, and that's something kind of flying around in space that gets drawn into Earth's gravity, gets pulled through the atmosphere, and sometimes hits the ground if it doesn't burn up. Early Earth's history, we didn't have an atmosphere, so that's kind of where we're headed with this. And actually, when we go to a place like Antarctica, Antarctica is cool for many reasons, pun fully intended. But one of the cool things about Antarctica is people go there and look for meteorites. It's one of the kind of hot spots for meteorite research, because if you're out on a giant ice sheet and you see something black laying on the ground, really only one way it could have gotten there, right? You're sitting on top of 2 miles of ice. If you see a little stone laying on the ground, pretty much came from the sky. That's kind of option number one, unless it's a different scientist throwing out their old field samples. And so when we take all these meteorites from around the world, but again, mostly from really icy and remote places, and we analyze them, they almost always come up with the same age, 4.56 billion years, because they formed at the same time that our solar system formed, and they've just been kind of floating around in space ever since. So now we've gone through this process where we've kind of built an Earth, right? And we built some other planets as well, but we're just going to focus on Earth. And one of the problems is that in early Earth history, the Earth has all sorts of ingredients in it, right? And it's also generating heat because of pressure. There's radioactive elements, and there's lots of radioactive decay, lots of confining pressure, and gases begin kind of working their way to the surface of the planet. And those gases in the beginning are basically hydrogen and helium because they're the lightest gases, and so they kind of come out first. And so early Earth atmosphere was basically wispy clouds of hydrogen and helium gas. But the problem was, anytime a strong blast of ions from the sun, we call it a solar wind, would hit the planet Earth, it would just blow the atmosphere away. There's nothing to protect it. And so all these charged particles coming from the sun blasting early Earth were pretty detrimental. So there essentially was, like occasionally an atmosphere. Really, again, this really thin, wispy atmosphere, nothing that you'd be able to breathe or anything. But then something very magical happens. We talked about the lightest elements in Earth actually working their way out, hydrogen, helium. The opposite is also true. So the heaviest elements, particularly iron, which is the highest abundant, again, it's a whole different class, we could talk about that. But iron and nickel in smaller percentages begins to actually sink towards the center of the Earth. So we start to get the differentiation of Earth into layers, which is really super cool. And so when we have this metallic area starting to build up in the center of our planet, parts of it, the very, very inside is compressed so much that it has to exist as a solid. It's forced into a solid because of the amount of pressure. And we call that the inner core. But outside of that, the temperatures are high enough, but the pressure is not quite high enough that all of this metal exists in this kind of sloshing, liquidy layer that we call the outer core. And the outer core is the same composition. It's basically a bunch of metal, but it's swirling around because of convection currents and heat. And what that does, and frankly, we've never been to the core, despite what Hollywood might tell you, it creates a dynamo, right? So once you have a bunch of spinning metal, you can actually generate a magnetic field. So you pick your compass out, probably not the compass on your phone. I've got a fancy compass laying around here somewhere, not on the table with me now. Your compass will actually, its needle will align to Earth's magnetic field. Earth is a giant magnet because of the sloshing outer core. Again, there's a lot to unpack there. Take a geology class. But when that happens, we now have this magnetic kind of protective layer. And as these ions, which are charged particles, are coming from the sun, they actually hit Earth's magnetic field, and it deflects them around Earth's magnetic field. So once we have that dynamo in place and that magnetic field in place, all of a sudden there starts to be able to be protection. So those ions, those solar winds can't hit Earth anymore. They're deflected by our magnetic field. Except actually at the poles, right? So the magnetic field, if you think about magnetic lines, why am I drawing with my fingers? If we have the Earth here, we've got these magnetic field lines. But that means that as those magnetic field lines are plunging into Earth's giant magnet, which you kind of think about at its core, there are basically these holes. And actually, as solar winds are traveling from the sun, getting deflected around planet Earth, some of them actually come into the Earth. Well, not that way. But they come in, can actually get into the atmosphere of Earth through these holes. And when they do that, they get really excited in a literal term, but also more figuratively, they get really excited about it. But they start to emit light. And actually, those are the auroras. So the northern lights and the southern lights are basically ion streams from the sun that are getting into the magnetic kind of cusp here. But that aside, that's just a cool atmospheric phenomenon. Once we have Earth's magnetic field, then gases that are kind of leaching out of the Earth, largely from volcanic activity, actually, in early Earth's history. It was a hot place, much hotter than now, so there was lots of volcanic activity. These gases begin to sit out here in the atmosphere, and they begin to pool up. They begin not sitting out in the atmosphere, they become the atmosphere, actually. And they begin to kind of pool up around Earth. And the early atmosphere, like the one that we're building right here, was primarily, as I mentioned, made directly from volcanic outgassing products, which again, hydrogen, helium, CO2, carbon monoxide, hydrogen, water vapor, so H2O, sulfur dioxide. A lot of these things that are present in modern day volcanic gases were basically filling the atmosphere. And those atoms begin to come together, right? And so we have large amounts of ammonia, methane, CO2, as I mentioned, water vapor, not necessarily a good place, right? So there's lots of ammonia and methane. Ammonia is cat pee and methane is farts, right? So pee and farts, not a good place to be, but also quite a bit of CO2. One of the things that we're going to explore in subsequent videos and subsequent weeks, not even this week, is that at this time, the sun, right, so this is still really early in the age of our solar system, the sun was about 70% as bright as it is today. Yet the temperatures on Earth were much higher than they are today, and that largely has to do with the percentage of CO2, which was much higher in the atmosphere in these concentrations, or much higher concentrations in the atmosphere at this time compared to some other things. So what we've done here is we've basically taken these explosions in the universe, right, in the galaxy, blowing all the stuff back out with stars exploding, and reconfigured them many times. In this case, we did it in a very selfish way because it's our star and our solar system. The early gases leaked out and were blown away by solar winds, but once we have differentiation of Earth's layers, and specifically the outer core, the Earth develops what we call the magnetosphere, or its magnetic field. That begins to deflect solar radiation, right, these ion blasts coming from the sun, and it actually allows this kind of now protected atmosphere to exist. So you could think, in the history of Earth and the evolution of Earth, the differentiation of Earth into layers is probably the single most important thing that's even made life possible, right? Okay, well, now we've got the start of an atmosphere, but we're not there yet, so I'll catch you in the next video.